surprising accidental discovery that clusters of galaxies, all of them, even actually just groups of galaxies, or that is Bremsstrahlung, that's free emission from very hot, highly ionized gas, but a very, very low density, just that there's such an enormous volume of it because it's a two-body process. You have an electron and an ion accelerating each other in ionized gas, so it goes to the density squared, then times the entire volume of the gas that's emitting. So even if the individual densities are very small, these volume, billions of cubic light years. A very high temperature is a surprise because you would not naively expect such hot gas to be able to be held together and confined unless you had a surprisingly large, enormous gravity, far larger than the gravity of the visible galaxies and stars that you see. It's the kinetic energy of individual gas atoms, such as hydrogen, the most common atom there, is, and that's 3/2 kT, that's 1/2 kT for each of the three dimensions of motion, in equilibrium, which we're assuming should apply, at least to some of these galaxy clusters, is going to also be the velocity dispersion of the individual atoms is going to be the same as the velocity dispersion which we already measured for the galaxies and found that it was shockingly too large. Well, the temperature also turns out to be too large. In fact, the random velocities of those galaxies is v squared. The velocity dispersion is very analogous to being a temperature of the galaxies. The second piece of evidence we've seen that there's much more gravity really requires dark matter. Maybe in some galaxy clusters things haven't settled down yet. Maybe stuff is escaping. Maybe the gas is just going to all evaporate away, although it seems to have been there for a pretty long time without going anywhere. But when you look at a galaxy cluster, this is our nearest big one. Remember, the Coma cluster. The cluster is fairly, quote, relaxed, so it should be in a virial equilibrium and a hydrostatic equilibrium. Everything looks fairly smoothly, roughly spherically distributed. It's common you see a giant CD galaxy in the middle, the most massive galaxy. It's settled down to the middle of the cluster, and almost everything in this picture is another galaxy in Coma. There's thousands of them. Mosaic of the X-rays is here, associated with particular galaxies. It just fills the entire space of the cluster that the galaxies also inhabit. Now, so when you do the arithmetic using the X-ray detections, to tell you how much gravity is present, and basically saying hydrostatic equilibrium. This is an interesting graph. I sort of already mentioned the result of this, but it's kind of interesting to see it in a fairly nearby galaxy cluster. This is in Perseus here. So obviously, as you go out to larger and larger radii, a significant fraction of a megaparsec, you're encompassing more and more of this galaxy cluster. That would be a typical size of a galaxy cluster here, hundreds and hundreds of kiloparsecs. And so the visible mass of stars, asymptotes up here, it looks like it's getting up to several times 10 to the 13 suns. However, as we said before, the gravitational mass is like 20. So all of that difference between the top curve here, where my arrow is, and then the visible luminous matter of stars, the baryonic material here, is dark matter? Wait a minute. We have not included, until the X-rays were discovered, we didn't include the large amount of diffuse mass from all of that hot gas there. It turns out to, this is amazing, it turns out to be often more mass than the entire visible mass of the stars and all the galaxies. Most of the normal baryonic matter in the cluster is in this hot intra-cluster medium there. Do they solve the dark matter problem? Did they come up with the missing mass? No, they did not. That's what you're really supposed to see in this diagram. They didn't solve it. They came up with more mass than before, but there was so much missing that even when you take into account the hot, thin gas, it still is not by an order of magnitude enough to hold the cluster together. So the difference between this middle black line here, and the total gravitational mass revealed by the X-rays or revealed by the virial theorem, if you want to use that older calculation, they give the same answer, is mostly dark matter here. That's a difference still of about a factor of 10. Here's one of the earlier X-ray spectra. Notice these are X-ray energies from 1 kilovolt. The Milky Way gets pretty opaque to softer X-rays at lower energies than that. Then you're up to 10 or 40 kilovolts up here. This would be like a dental X-ray. There you see this characteristic bremsstrahlung spectrum. And what's the spectrum of bremsstrahlung? The brightness is e to the minus h nu over kt, and so you're looking for this exponential rollover here, which you can see is around, I don't know, 5 kilovolts there. So that's what tells you what the temperature is, millions. But you notice something else rather unexpected, also not predicted in this X-ray spectrum. In addition to free transitions that makes this continuum, there are also transitions where an electron starts free, hooks up with, and recombines with the ion. This ion has like almost no electrons left at all. So the electron recombines not to one of these outer electron orbits. That would be a relatively small energy. The electron recombines all the way to one of the innermost, most closely bound orbits of, say, iron. A photon of that particular energy difference can be emitted. Actually, the electron might start at a high level, but eventually it ends up at a very low level, so a bound trend. By this process, you expect, if you have heavy elements present, you expect to have some very strong high energy emission line. But now we have the measure of how much ionized gas is here, which is mostly hydrogen, and we have the measure of several heavy elements, and we can see what is the proportion of heavy elements compared to hydrogen. Now, you might have naively expect just leftover primordial gas, 90% hydrogen and about 10% helium, and then almost nothing else. And yet, contrary to what everybody was expecting, there's a lot of heavy elements in this diffuse X-ray gas that's filling these clusters. What does that immediately tell you? This, whenever you see iron, nuclei in particular, like iron in your bloodstream, it only has one possible origin, supernovas. Almost all of this gas was once inside stars. It was once inside galaxies. It went through these cataclysmic supernova explosions a long time ago, and then, it's amazing, it was expelled at high velocities out of these galaxies, but it didn't have escape velocity from the cluster because of all that dark matter. So it's just hanging around there as a very informative, revealing fossil of all of this nucleosynthesis activity billions and billions of years ago. That accounts for a lot of the known baryonic material in the universe. This was another accident. Such a large amount of gravitational mass, even if it's unseen mass, it's going to curve the paths of light rays of background objects that happen to pass close by. This massive cluster full of dark matter focuses light beams that were originally just going parallel and converges them like a lens, gravitational lens. One of the consequences of relativity is that what we think of as straight lines, or what we think of as space-time, actually is warped or distorted by the presence of a large gravity, a large mass, in a small place. If you have a background light of a distant galaxy that passes very close to a black hole, the black hole would be right here. It gets inverted, highly distorted, and you can actually get pairs or quads of images depending on how the mass is actually distributed. It's a very simple case of just a single point, a black hole. A more realistic case would be if you have a whole cluster of dark matter, and then you get these more interesting pattern. This is an attempt to show you how strong the gravitational lensing effect can be if you have a lens, which could be a galaxy with a lot of dark matter, or more likely a galaxy cluster with a ton of dark matter here. Here is a star as it actually is behind it. And then over on the right-hand side, the astronomers observing from Earth does require a very lucky coincidence of foreground lens and background object lining up directly along the line of sight that happens to pass towards the Earth. Then you get this deflection angle alpha. The angle, that's the gravitational deflection, 2 gm over r, that's the escape velocity squared, compared with the speed of light squared. Actually, there's an additional 2 that Einstein predicted that you would not have guessed just by using Newton's laws. Anybody remember, if you have a light ray passing right along the surface of the sun from a distant galaxy or quasar, and then traveling onto the Earth, how much does the surface gravity of the sun deflect the light beam? This was the proof of Einstein's theory. Remember, during those famous eclipse expeditions to observe how much the stars appeared to be deflected up to here, away from the sun's position during an eclipse? How much is the angle, maximum deflection angle, that the sun's surface gravity gives you? 3/4 of 1 arc second, because the escape velocity from the surface of the sun is a lot less than the speed of light. Big cluster of galaxies, these angular deflections can be like 10 seconds of arc. You see a bunch of old galaxies, mostly elliptical galaxies, very few spirals in the center of this very dense cluster. You know that there's a sea of dark matter that you don't see. The heck are those blue streaks? That turns out to be the light of a background galaxy that fortuitously just happens to be lined up almost along our line of sight, but directly behind this galaxy cluster. And so it has been stretched out, just like I showed you that distortion of the Smithsonian picture. These are all images as a lens can form, a converging lens can form images. This kind of lens can form multiple images of the same darn galaxy. That's all the same galaxy, just distorted by different amounts by all this dark matter. This whole cluster is a dark matter telescope. It's a dark matter magnifying lens. I'm lucky, and there happens to be a galaxy which presents itself behind this lens. I can get a high magnification view. In the best cases, it could be 30 or 40 times magnified compared to what it would normally be. Also, you learn more about the gravitational potential of the dark matter, how it's distributed, that's causing. So you learn about the lensed object and the lensing objects as well. There's extreme distortions for the light that passes very close to the galaxy cluster. If you go further out, so you're some distance away from the dark matter here, these are background galaxies mostly also. Their light is also subtly distorted by the same gravity of the dark matter mass here, just a little bit. They're stretched out a little bit. This actually means space and time are stretched out a little bit, just like a few percent azimuthally. They actually discovered this effect by averaging small distortions of the images of hundreds of galaxies. These are the average tilts or major axis of galaxies. That tells you pretty accurately the total amount of dark matter in here. This doesn't require this gravitational mass being baryons. It doesn't require it producing X-rays. It doesn't require the gravitational mass being in hydrostatic equilibrium. Direct measure of how much mass is there in any form that has gravity, including dark matter, with no assumptions, except that Einstein is correct, confirms the very large masses and the very high mass to light ratios that the X-ray astronomers and the optical astronomers had already been saying for like decades. Now we know for sure there's no way out of it. Reconstructed from weak lensing distortions. That's the dark matter around this cluster. It looks like there's sort of two concentrations. Maybe they're coming together. By the way, you can see the galaxies. The optical picture there of the orange light is the light of galaxies, and it looks like there's two concentrations of them too. So in detail, the gravitational lens map confirms what you already thought. The light blue tint is the reconstructed distribution of dark matter, and then the visible picture shows you it follows pretty closely the distribution of the normal visible starlight of the galaxies, except you need mass to light ratios of hundreds to produce such strong gravitational lensing as is seen. In most cases, you can reconstruct the gravitational lens map. I've already showed you a bunch of those pictures, and you can compare it with the reconstruction from the virial theorem or something like that, and they usually agree with each other. There are a few spectacular cases where they don't. Those things are probably in motion. This is like one of the most famous pictures of the last 10 years. Have anybody seen this bullet cluster picture? Well, if you have, I'm just going to show you. Here are two clusters of galaxies which went through each other. This cluster here and this goes here. You can see the galaxies. The blue shows where the dark matter is from lensing. The red shows where the hot intra-cluster gas is. This galaxy cluster started out on the left side, and this galaxy cluster started on the right side, and they literally just moved through each other, but the hot gas couldn't do that. The hot gas got shocked and lagged behind. In fact, it actually really looks like a shock wave, a bow shock here, is tearing that hot gas. That's shown, the X-rays are shown in pink here, away from the cluster of galaxies here. So you can see the mayhem. What about the dark matter? We had two clouds of dark matter, this blue cloud here and that blue cloud there, passing through. See, one cluster was moving from right to left, the other from left to right. The dark matter passed through without any disturbance. The hot gas strongly pushed back by the interaction with the other hot gas. Dark matter didn't care. This is the strongest piece of evidence, the weird nature of dark matter, that it doesn't have much interaction with itself. Simplest possible explanation of dark matter, to stick with something we actually know. We know there's lots of low mass stars in the universe. Let's just postulate that there's certainly planets. It's virtually invisible. It has gravity, it has mass, but that's about all it has. And at least we know they exist. The problem, of course, is you would need thousands or millions of Jupiters for every star that we know about if you want to explain all of the dark matter. They're massive compact halo objects, a great acronym. All we have to do is look for the gravitational lensing signature of these Jupiters. Just look in any direction out of our galaxy, and every once in a while, there's so many Jupiters, allegedly, for the dark matter, one of the Jupiters will by accident pass exactly in front of a distant background star. It will gravitationally magnify the normal size of the background star, which is very small, and it might make the star appear to be 10 times bigger or so. So for maybe a few days, that star will appear to be 10 times brighter, and then, they move on, they have random motions, and the alignment won't be perfect anymore, and that star will just fade back to normal. His plan is to search for a 1 in a million effect that could never be reproduced, because this star will be brightened one time and that's it. It's an irreproducible effect. We're going to monitor millions of stars every night. Not only did they do it, and this is the thing, I never would have believed this, but they did discover gravitational lensing events. They proved that this microlensing is a real thing, but they only found a small number of them. Much less than what would be if the dark matter halo of the Milky Way was made out of machos. That leaves us with only one other thing here, and this is another great acronym. They have no normal interactions with matter because they're not made of protons, neutrons, and electrons. They have only gravitational interactions. Maybe they have some weak interactions which maybe led to their being formed in the Big Bang. They have to be massive particles. They seem to have no other effects. They're so hard to even tell that they're there. We're going to call them weakly interacting massive particles, WIMPs. Got to be one of the most perfect acronyms ever. We already had an example, by the way, of a WIMP. So at least it wasn't totally ridiculous. We know that during the Big Bang, and we'll find out more about that in the last week of class, that the universe formed through only weak interactions, an enormous sea of vast quantity of neutrinos. They have almost no mass. They have virtually no interactions with anything except weak interactions. So they're doing like nothing now. And amazingly, at least some of the neutrinos do have a little bit of mass, but probably not enough mass, I'm sorry to say. So the neutrinos are not really a good candidate for the explanation of most dark matter, although they do sort of point the way. There must have been some other particle, very likely not yet discovered by modern science, unknown to humanity, which may account for most of the mass of the universe. This is such an outrageous conclusion. I would never believe this if the overwhelming amount of evidence left us no other choice but forces us to the conclusions. Postulated particles that could produce during the Big Bang, depending on your theory of particle physics. One of the most popular predictions that goes a little bit beyond the standard model is some particles that nobody's ever seen. They've only been postulated to exist, called axions. The thing that's so cool about this is that the theoretical predictions that axions should exist from the Big Bang was made by Roberto Pache before he became dean of physical sciences at UCLA. So there is a serious chance it would be so cool that UCLA basically just discovered what most of the universe is made of. Massive is a bit of a misnomer. The mass might be less than an electron, which, you know, is really pathetic. And that could still do the job. It's just that they're not zero mass particles like photons. That photon is massless. We have very little constraint on what that mass would be. Like I said, it could be the mass of an electron. It could be a hundredth of that. These massive particles, then, if they are the dark matter, are passing through this room right now. Or they're passing through your room too. You don't have, you know, enough light years of lead to shield you from them. So they're passing through laboratories all around the Earth, and they're passing through underground laboratories deep below the surface of the Earth where no other particles like cosmic energy rays and things like that could get to you. And so people may discover them passing through their laboratory if you have very sensitive weak interaction detectors. This kind of stuff that detected neutrinos, except just much better and much bigger and even much more expensive. That may work. And each one of these experiments is sort of sensitive to different masses of particles, and they keep ruling them out. And they get better and better. The limits are getting more and more strict. Still hadn't found it. One of the astronomers, I think this is in the 40s, look at this galaxy. It's a normal spiral galaxy. We're looking at it kind of face on. There's a normal spiral galaxy here. Here's a normal spiral galaxy that's edge on. You can see the dust lane there. What's weird about these galaxies? They all look like they've got a star in the middle of it. What the heck is that? And it's right in the middle of it. It's never to the side. It's right in the middle. It's not a star at all. It's not even made of stars. Why? Because it does not have the spectrum of a star. It has no absorption lines at all. In fact, the spectra that Carl Seifert took, it has weird stuff that I've never seen anywhere else and never predicted. It has a bunch of strong emission lines, so that means hot ionized gas, and they have enormous ranges of Doppler shifts. They're broad lines indicating ridiculously high velocity motion. Ignored by astronomers for 20 years. Accidents happened to the right people. And what was the invention of World War II? Radar. They started detecting radio waves from deep space. Never predicted by anybody. No clue what the heck it was. It turned out that they were picking up synchrotron emission, which they didn't even know what that was. So that requires extremely high energy, high speed electrons moving around at almost the speed of light in the presence of a magnetic field. They went to an enormous amount of work to localize the exact direction that these sources of radio waves were coming from. How do you know where a source of meter wave radio waves is coming from? Diffraction limit, lambda over d. Lambda is so long for these radio waves that you cannot localize what direction they're coming from better than an angle lambda over d. So until you come up with a way of making radio antennas, not World War II antennas, but antennas that would be like kilometers in size, you really couldn't tell where the radio waves were coming from. Synthesize the effects of a kilometer-size antenna by combining in phase the signals of individual radio antennas as an interferometer. Finally, they could localize within, a minute of arc where some of these most powerful radio sources were coming from. And where were they coming from? The centers, pretty much, of galaxies. The weird galaxies that had those weird stars in the centers of them that Carl Seifert and Fritz Zwicky had noticed. there's something not about stars at all in the centers of galaxies that produces these incredibly bright points of light and also produces radio waves and a bunch of other stuff that galaxies are not supposed to be producing also, such as X-rays. It's something that can only happen in the nucleus of a galaxy, nowhere else. You could call them Seyfert galaxies if you want to honor Carl, or you can call them active galactic nuclei. What if you had a more powerful version of this where the star was maybe, I don't know, 10 times or 100 times more powerful, more luminous, so you could see it at a large distance? This is a relatively nearby galaxy in our local neighborhood. But what if you could see this thing? It would look pretty much like a star, unless you looked really carefully, as I did in my for part of my PhD thesis. You looked really hard, you might see a little bit of fuzz around the star. It would look quasi-stellar. So what the radio astronomers had accidentally found and localized was bright, powerful versions of Seyfert galaxies. That was really the most incredible shock about the quasars, or I should say the quasars. The first ones that were found have outrageously high, the highest known at the time, redshifts. A large redshift could only happen in an object that was very far away because of the expansion of the universe. Well, if it was very far away, then that means that it must be intrinsically outrageously luminous. It is 1,000 times brighter than the entire luminosity of an entire galaxy. These are the finest measurements that have been ever made of the brightness of an active galactic nucleus as a function of time. Do you see what I've got on the vertical axis? That's brightness. And on the horizontal axis here, that's days. Each of these dashed vertical lines is 3 months, always changing their brightness in a non-periodic, non-predictable, seemingly random way. Here's another object that we did with Kepler. That one didn't do some stuff for a while, then it went up. Here's another random one there. It's a little bit fainter, a little noisier. Applies to quasars, which have enormous power. They might be outshining the Milky Way galaxy by factors of hundreds. And yet, they manage to be continually randomly changing. That tells you an upper limit on the size which is emitting all of that light. Let's suppose that you had an object that was completely outshining 100 Milky Way galaxies, but you see that it changes its brightness output substantially, like you saw in those pictures I showed you of actual data of actual quasars. What if it changes its brightness in a time less than 1 year? Which is true of all of the ones I showed you. You're not actually looking at all of the object at the same time because of the finite speed of light. The Earth is way off here, maybe a billion light years off here to the right. We're seeing the light from the front side of this object more recently, and the side of the object we're actually seeing as it was earlier. Anyway, the light from the back side of the object is even more delayed. So we don't actually see all of the different parts of the object at the same time. And yet, for all of these parts of the object to simultaneously get brighter or simultaneously get fainter, and for us to see this change within less than a year, it means that the size of the object is less than the distance that light can travel in that time interval. D, the size of the object, it's less than or equal to c, the speed of light, times the amount of time the object takes to change its brightness. D is less than or equal to c times delta t. Greatest feats of amazing mystery in all of astrophysics, how so much power could be generated in such a ridiculously small volume of the center of a galaxy. And there is no way around this. D is less than or equal to c times delta t. You can take that to the bank. These are ridiculously compact objects. That's the one most important thing you need to know about active galactic nuclei.